Hi everyone, Dr. P again, and in this video we're going to look at hydration of alkenes. And this is actually sections 8.4 and 8.5. Let me just double check that. Yes. Now before I do that, let's just take a brief moment to go back and take a look at halohydrogen formation again. So let's take the following alkene, and I'll go ahead and do Br2 and H2O. You could use Cl2 if you wanted to, and I will get I'm just going to write plus En for plus enantiomer, because depending on which side the OH adds to, we'll either get the bromine on sticking one way or the other way, because that carbon there is chiral. It has a hydrogen, a methyl, a bromine, and that stuff. This carbon is not chiral because it's got two methyls. All right. Now notice that I added the OH specifically to the more substituted carbon. So we'll say here, nucleophile adds to more substituted carbon. Okay, and in this case, I'm going to say weak nucleophile. I'm going to add that in there, weak nucleophile, because we'll see some cases where actually we get kind of the opposite going on if we use a strong enough nucleophile. So why would this be? Okay, again, I didn't talk about this in the previous lecture video, but let's take a look at why this might be. So let's go ahead and make the, let's do it this way. Let's go ahead and do our mechanism. And now what we'll get is, I'm going to draw this a little different here. I'm going to draw BR like that. So I'm going to look at this from a different, got my CH3 and my CH3, and over here I've got my, we'll just do it like that, my CH3. Okay, so I'm looking at it kind of from one end instead of more from the top like last time. Now I've got a positive charge on the bromine, but bromine is happier, if you will, with a negative charge. It's has a decent electronegativity. So what we're actually going to see is these bonds are not of equal length, and so we'll actually get we'll have a partial positive on the bromine, and then a bit of a partial positive on the carbon there, and then this bond is a bit longer. It's kind of stretched a bit. So now our weak nucleophile can go ahead and add to the carbon that has more of a positive charge. Why does it have more of a positive charge? Well, it's more substituted, so it stabilizes that positive charge better. And those electrons can go up there, etc. Okay, so I did want to talk about that because we have to think about this. This is actually an extension of Markovnikov's rule. Okay, the most stable intermediate or transition state is going to be the one that forms. And this becomes important when we look at hydration of alkenes. So let's look at some ways that we can hydrate alkenes. Now, what is a hydration reaction? So I'm going to call this acid-catalyzed hydration. Okay, and let's go ahead and take our asymmetric alkene here, and I'm going to treat it now with water and acid. And I will get that species there. Now, we could look at this, maybe look at this a little bit differently here. Let me draw this out again. You know what, let me do this in a different color here. Let's do HOH. And with an acid catalyst, we will get the hydrogen adding to the less substituted and the OH adding to the more substituted. Now, I forgot to mention that this guy here should be an equilibrium arrow. This is actually an equilibrium reaction, and there's some problems with it. At high temperature, that's going to actually favor the reverse reaction, which is a dehydration reaction. So this is not necessarily of great use synthetically, because it can be difficult to control. All right, now let's take a look at what this mechanism would look like. Now, I drew it an awful lot like the addition of HBr, and that's because, well, it is conceptually very similar. Okay, we have some source of H+, so I'm just going to write H+ there. There's my H+. And I will come along and grab the H+. Often it's in the form of H3O+. It doesn't have to be. It could be something else. And let me put in a hydrogen there just to show you. Hydrogen, hydrogen. And now I've got my positive charge. And now I can have my water, which is present, and that can add in, and that gives me now boom, 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 boom. It helps when you make the sound effects. O, H, H, lone pair, positive charge. And now another molecule of water can come along and deprotonate. And that gives us now boom, 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 OH. And of course I have my hydrogens there. So this is a Markovnikov addition. In that the hydrogen goes to the less substituted and the rest of it, the OH, goes to the more substituted. Now we'll end up getting a mixture of products. In this case, this product is actually doesn't contain chiral carbons. But if there were chiral carbons, we would get a mixture because where is it? Here we go. The carbocation is planar, so the nucleophile could add into either side. So we'll get a mixture of products. So it's not an anti-addition like the bromination. So that's something important to remember. Now, are there better ways to do this? So I wouldn't mind doing this in a lab as long as I control my conditions carefully because, well, I'm not using anything too nasty. But there is something that will give us a Markovnikov product specifically, and that is oxymercuration, de-mercuration. And this is not something I would like to do because it uses mercury. So this is actually the regular direct hydration, acid-catalyzed hydration is mentioned in, I think it's what, figure 8.4, but then figure 8.5, this is in section 8.4, goes through the oxymercuration, demercuration. And so in this case, let's see here. Let's do the following. Let's take our same alkene. And so what I'm going to treat it with is HgOAC2 and water. Text also says THF, but we'll ignore that. And then NaBH4, sodium borohydride. And what we get is a hydration. We add a hydrogen to one end of the double bond and the OH to the other end of the double bond. And this is Markovnikov addition. Interestingly, it's also an anti-addition. So if, for example, I have the following and I treat this with HgOAC2H2O followed by NaBH4, I will get let's see here, I'll have that, and then I'll have my OH, here. Let me just make sure that I'm doing that correctly. Am I doing that correctly? Yes, because that goes in, that pops out, yeah. And I can actually get the other version, so if it attacks the other side, it would be OH over here, and then the methyl, and then that guy there. So my OH, and then I'm not showing the hydrogen that's being added. Maybe I'll add that in. There's H there, and we'll add it in H there. Those are my dashes there. So my OH and my H are anti to each other. We actually refer to that kind of orientation, whether they're on different sides or the same side, as stereochemistry. Markovnikov's rule is an example of regiochemistry. That is, where on the molecule the addition occurs. So the OH is added to the more substituted instead of the less substituted. That's regiochemistry. The OH and the H are added to opposite sides, an anti-addition. That's stereochemistry. So let's take a look at the mechanism. At least partial mechanism. So I'm going to go ahead and, yeah, let's use this guy here. Why not? And initially, we use our HgOAC2. Well, first of all, what is HgOAC2? It's OAC, so it's Hg, and then attached to two acetates here. And this tends to actually form a covalent type bond. And so when I have my HgOAC2, so I'm just going to write it as HgOAC-OAC. So the AC refers to the acetyl here, the CH3C double bond O. And I'll go ahead and I'll have attack by the pi electrons from the double bond. And then I'll also get electrons from the mercury itself adding in, which I'm actually not going to show here, so this is going to look a little weird. But what I get is I get this mercury ion here, a mercurinium ion. And now I can go ahead and have any water present. And that can come along, and let's just have it, I'll have it attack the top one up here, and that pops open, giving the following. So this is going to be from underneath, so that would then be OHH, positive charge, and then this guy, the methyl that was pointing back, is going to be sort of flipped up. And then I'm going to have here, I'll have my HgOAC, and I'll have my other methyl like so. Now another molecule of water can come along and deprotonate and that will give me now, remove this so we can take a look here. And then in the final step, which I'm not going to draw the mechanism for, but in the final step, or rather the second part of the reaction. So whenever I write like 1 and stuff and 2 and stuff, that means they're two separate steps. First we add the HgOAC2 with water, reaction occurs, then we'll add NaBH4. And so adding the NaBH4, sodium borohydride, reduces, so it's going to have a hydride replace the HgOAC, and we will end up with OH, and that guy's up like that, and then the other guy is down like that, and we have a hydrogen that's replaced the HgOAC. And so this one, if you actually look at it, is this guy just flipped over. Okay, so this shows the anti-addition because, well, we have, what's this? This is a three-membered ring intermediate. And in this intermediate, it's like the bromonium ion. And so whatever we're adding, this ring pops open and is anti to. It's on the opposite side of the, the plane of the, well, what was the double bond, but in this case, the ring. So we get an anti-stereochemistry. Now we also get the Markovnikov regiochemistry for the same reason that we did in the, where did I put it? Here it is. In the in the halohydrin formation. So again, we'll go ahead and get the OH adding to the more substituted, because that's going to do a better job of stabilizing positive charge from the mercury there. Okay. Now there is another hydration that I do want to talk about, but this lecture has gone on for about 20 minutes, and I think now's a good time to stop. So in the next lecture, I'll actually talk about a hydration that gives an anti-Markovnikov product. It gives the opposite of the Markovnikov regiochemistry, and that's hydroboration oxidation. So we'll take a look at that next time. Until then, stay safe. Bye now.